Ben, you want to? Whenever you're ready, Ben.
Yeah. So if you guys don't want to be recorded, you can just turn off your cameras, and we'll cut off this first section if you want. Also, we'll try to read out the questions for those of you who are watching this recording. If you have any questions that you want to ask us that someone hasn't already asked, you can feel free to ask them on the Discord as well. But we can start with the introduction. Gets next. So,
Hey everyone, I'm John. I'm president of ACM AI, and I just wanted to give a quick 2-minute introduction to what ACM does, or ACM AI does, in case you may have missed our first general meeting. So our mission as an organization is to build and develop a community of students who are interested in AI at UCLA and beyond. We are one of 8 subcommittees of ACM, and we're focused on artificial intelligence. Next slide, please. Our values are as follows. First, technical proficiency and awareness in AI. All of our events, our projects, our workshops try to increase either your ability to build your own AI or your awareness of its impacts on the world and society. Second is creating a positive impact on society. It's something that might seem pretty obvious, but it's easy to get wrong, especially since you're in advanced track. You'll probably learn in a little bit that it's actually quite easy to not intend to do anything wrong, but make AI that, for instance, might discriminate against minorities. So it's very important that we consider a lot of societal and big impacts that technology we build might have. And lastly, our third value is diversity and inclusion. AI is something that affects everybody, and we want to make sure that everybody has access to a good AI education. This is regardless of your background, whether you're a CS major or not, whether you come from a rich or poor background, whatever it might be, you deserve to have a say in how AI is built because it affects you. And so, can you go to the next slide, please? We have 4 major initiatives that ACM AI works on to try to accomplish this mission and fulfill our values. First is workshops. So for example, advanced track, you're here right now. We put on workshops to teach machine learning skills to UCLA students. Second, we have projects, which is an initiative to give students an opportunity to get hands-on experience with applying machine learning to real-world problems. You'll hear about this more in a little bit from Harsh. Third, we have events, which puts on various one-off events related to AI for UCLA students. An example of this might be Demystifying AI. You might have seen some advertisement for it recently, which is just a non-technical introduction to AI and its ethical impacts. And lastly, we have our outreach team, which works on doing AI, raising AI awareness beyond UCLA. So examples of things that our outreach team works on is our You Belong in AI podcast, which is focused on diversity and inclusion in AI, as well as our high school course, which teaches introductory AI to high school students. So these are 4 of the main initiatives that ACM AI works on. If any of these things are interesting to you, feel free to reach out to us at any time on our Discord or Facebook page or whatever it may be. And yeah, thanks for all your interest.
Thanks, John. And now I'll introduce ourselves. People helping out with officers or with advanced track is me, Ben Limpanukorn. And then we have.
I'm Justin. I'm a 3rd-year CS student. My pronouns are he, him, and I'll be helping out this fall.
Yeah. Hey guys, I'm Paymon. I'm a 2nd-year CS student. Pronouns he, him, and I'll be another one of the officers helping out this quarter.
Hi everyone, I'm Vaishnavi. My pronouns are she, her. I'm a 3rd-year CSE major, and I'll be helping out with advanced this quarter as well.
I forgot to mention I'm also a 4th-year CS major. So we can go to our overview and the logistics. I know, Justin, you want to talk about the difference between beginner and advanced workshops?
Sure. So we are currently teaching the advanced track. So this is kind of the sequel to our beginner track. So in our beginner track, we intro just the basics of machine learning methods, like linear and logistic regression. No worries if that's a little hazy right now. We're going to be going into a quick review of that. We would be explaining the mathematical concepts and motivations behind ML. we'll be introducing neural networks in beginner, and then there's no prior coding experience required in beginner. So that's kind of a jumping off point for advanced, where we're going to be diving into sort of more advanced topics within neural networks, deep learning, and different architectures. Another workshop that is actually debuting this quarter is Apply ML. And I think we do have one of our officers here. If we can get to the next slide, just to intro it a little bit.
Awesome. What's up, guys? Thanks for the intro, Justin. My name is Harsh Chavisa, and my pronouns are he, him. I'm a third-year CS major, and I'm one of the officers that's going to be teaching the Apply ML track this quarter. So Apply ML is for anybody that's really, really interested in the direct applications of machine learning. I think we found that beginner and advanced track do a fantastic job of covering theory, but don't always go over all the different applications and all the steps to making a ML pipeline and ML model. And that's what we're looking to do. And that's what we're looking to teach in Apply ML. So we're going to be teaching you how to visualize your data, how to implement a model, and then at the end, how to evaluate your model. And we actually just already had our first meeting. It was last Thursday, but our second meeting is this Thursday from 6 to 8. And, if you have some time, we'd love if you could come out to that. And our first meeting is on YouTube in case you didn't get a chance to come out and you want to catch up. Awesome. So along with having the opportunity to teach Apply ML, I also have the opportunity to serve as projects director this year for ACM AI. And our goal for projects is to really create a more inclusive projects team, which will allow more people, even if they don't have as much experience with AI or ML, to jump in and really work on their first end-to-end machine learning project. So this year, we're going to be working with the Daily Bruin to create an automatic system that will predict, given a pair of two articles, which one will receive more views. And we feel that this engine will really help the Daily Bruin maximize its readership, because they can then pick which articles are going to get the most views and then promote those more heavily. So if this sounds interesting to you and you want to join projects, I have some good news for you. We're going to be taking people on to join projects during winter quarter and spring quarter. We are, however, making it a hard requirement that you must take advanced track before you apply to join projects. So all you guys here are perfectly in line for that. So everybody here is taking advanced track right now, which means you'd be eligible to apply for the projects team during winter quarter. If you decide not to take advanced track this quarter and you decide to stick with beginner track, you can take beginner track in the fall, then take advanced track in the winter, and then finally apply to the projects team in spring. So if, like I said, if this is something that interests you, please keep an eye out for those applications when they come out during winter and spring, and make sure to finish advanced track before you apply. Thanks so much, guys. Really appreciate your time. I want to hand it back over to our awesome crew now that's going to be teaching you some advanced track.
Awesome, thanks, Harsh. So on the next slide, we're going to be getting into our tentative schedule. So this past summer, we kind of revamped our curriculum, trying to make it more friendly toward a virtual environment. And that includes the addition of a guided project. So you'll see in week 7 and week 8, we have a guided project for you guys. So hopefully that'll be sort of maybe even like a little taste of what you might do in Apply ML, where we are applying hopefully what we've learned within the course of the workshop to an actual project. And then we are always meeting Monday 6 to 8 for 8 weeks this quarter. So some expected prior knowledge for jumping into advanced track. We expect you guys to be comfortable with coding, have some sort of basis for machine learning, and a basic working knowledge of working with data, especially NumPy arrays, because we're using Python. So today we're going to be taking it easy. We're just going to do a quick review of machine learning itself, a little refresher on linear and logistic regression, and then just touch on the basics of neural networks. And before we go any further, are there any questions that we have? Feel free to unmute yourself if you're comfortable as well. If not, we can go through the chat.
Since these questions aren't recorded, I think I'm going to read a couple of them out loud. I won't read your names. One person asks, which language were we using in advanced track? And the answer is we're going to be using Python. The online compiler. Oh yeah, and once we get to the last few weeks, you don't have to worry about setting up any environments until we get to around, we'll give you instructions early on, and then we'll also go over how to use PyTorch in detail in one of our workshops. If you have any other questions, feel free to ask them in chat or unmute yourself like Justin said.
Awesome, thanks, Ben. So if there are no more questions, then we can move on. So we're going to be going into a quick review of linear and logistic regression. Next slide. So let's think big picture. Machine learning is using data to teach computers how to answer our questions. So if we think about this, this is inherently different from how we would view traditional programming, wherein we as developers would take data and a program, send that into a computer, and then have an expected output. Machine learning is kind of switching this paradigm and taking in data and an expected output to give us a program. So this is pretty novel, and this is why you guys are here. Next slide. So the different types of machine learning. So we, for the majority of this workshop, will be touching on supervised learning. So supervised learning is when we have labeled data pairs. So we have data and then labeled outputs. We have direct feedback to our model, and we are usually looking at prediction tests. Other subsets include unsupervised and reinforcement learning. So unsupervised, like the name suggests, there's no labels, no feedback, and we're trying to find hidden structures or patterns within the data. And reinforcement learning is trying to get a model to act on a environment using decision process and rewards to learn a series of actions for an agent. So again, we'll just be touching majority on supervised learning. Next slide. So some key elements of machine learning is representation. So how do we represent this wealth of data that we have? So again, data is worth nothing if we don't have a concise and useful representation for it. So this can be in the form of decision trees or neural networks, which we'll be talking heavily on later in the workshop. So here we just have a very simple decision tree. Our root node is weather, so it'll split if we have some sort of categorical data into sunny, cloudy, and rainy weather. And then just going down from there, we try to just partition our data into different classifications and predictions. Next slide. Evaluation. So what are the metrics and what are the methods in which we evaluate our programs? So examples of these are cost functions, taking margins, looking at entropy and the squared error of our residuals. So this is a very simple confusion matrix. So this is for a prediction task. So as we can see like selectivity, specificity. These are some things that we will be going into when we're actually evaluating models, and hopefully something that you guys will be using when we get to that guided project. And lastly, optimization. So this deals with combinatorial problems, gradient descent. So in this example, we have the traveling salesman problem. So just different algorithms that might be computationally intensive. We can use the power of AI and machine learning to kind of help us and expedite our process in solving these difficult problems. So today we'll be talking about two very large problems in the domain, specifically classification and regression. So classification, just going off of what the name says, it's a task sort of like identifying a digit. So imagine we have a data set of a lot of handwritten digits, and we want a computer to be able to tell us what digit this is. So the computer will get this raw input of a 9, and we'll feed this into our classification model, and then it'll give us a vector of probabilities that correspond to each class. So as we can see, the probability for the number 0 would be 0.05. The probability that it's a 1 is 0.01. And then we continue this until we get to the number 9, where we see a noticeably higher probability. Another problem that is common in the field is regression problems. So this would be something like predicting house prices. So in this case, we would have a model, in this case, a linear regression model, and our input would be the square footage of the house. So let's say we tell the machine that we have 4,000 square feet, we feed it into our model, and then we expect to get a continuous range of prices. In this case, just under 200,000. So going into what linear regression is, we've all had our very basic science classes where we have to make a best fit line to some experiment that we ran. So this is kind of in the same vein. Our goal is to find the equation of a line that best fits our data. So this is particularly in 2D space. So we want to be able to use this to extrapolate and predict outputs from inputs that we haven't yet seen. So in this case, notice that our outputs are continuous. Like we have a line that we can both extrapolate and interpolate from. So in this case, we have more an output that's better suited for a regression problem. So if we can imagine our x-axis being square footage of a house, when we plug our input of a square footage into our model, the equation of the line, we can expect to get a price, continuous price.
Right. All right, so now we can go into a few of the details of linear regression. The first thing we want to talk about is the hypothesis function. Earlier on, we said that with supervised learning, the idea is that we have an input space and an output space, and we want to compute a function that maps that input to output. The problem is, like, what is that function? What can that function be? Right? We can make it be, it could be any possible function, but trying to optimize or trying to find, trying to search for an optimal function among that wide space is kind of difficult. So what we do is we restrict it to, or in this case, restrict it to a specific format. For our single feature, for a linear regression at least, with a single feature, we have our hypothesis is just a line, right? Where x is a single scalar and a weight is a single number plus a bias. So this should be familiar, like anybody who has taken an early math class. But with multiple features, the idea is similar. Each of these x values, x1, x2, all the way to xn, those are also scalars. Each feature might represent a different part of the input. Like, let's say we were trying to predict the amount of rainfall based off of temperature and humidity. You might have two features, temperature and humidity, and those are two numbers, x1 and x2. In this form, we're representing them as like scalars and then adding them together. But later on, you might see them also represented as a vector. So x1 to xn is a single vector x. And the bias is also, and the bias and the weights are also represented as a vector. So W here are the weights and B is the bias. So instead of searching through all possible functions, what we're doing here is searching through all possible linear functions. And the parameters that we're changing to search through these functions are the weights, W, and the bias B. So now that we have a hypothesis function, we need some way of evaluating how close our hypothesis is to our ideal solution. Basically, how poorly does it perform on the data that we have? And to do that, we have a cost function, or also called a loss function. what this does is it computes the difference between our predictions, y hat, and the ground truth, y. The greater the difference, the higher the loss or the cost. This specific function, so there's more than one possible cost or loss function. The one we're showing here is mean squared error. It's a commonly used one. One reason that's commonly used is because when you take a derivative, it's pretty straightforward and works well. But in this case, it's called mean squared error because it's taking the error, which is y hat minus y. It's taking the square of that to make sure, like, if it's less than or greater than, it's the same thing. And then it's taking the mean. So m is the number of samples. So it's taking the average across all of our samples. So an example of this would be like if you're trying to predict the temperature for like today's temperature, and the actual value was like 100 degrees, but our prediction was 50, then the difference would be 50, and then you square that, you get like 2,500 or so. And you do this for across all the samples to get an overall loss, to kind of score how well your hypothesis function is doing. Whereas like if you had a prediction of 99 and the ground truth was 100, then the difference would only be 1, and so the cost is lower. So now that we have a way of evaluating it, we need to figure out how do we, and we have a way of evaluating our hypothesis function now. We also need a way to use that evaluation to adjust our hypothesis function so that it reduces the loss. And that's the algorithm where we're going to show here is gradient descent. There's other algorithms possible that you can use, but we're going to use gradient descent because it kind of leads nicely into neural networks. The goal here is to minimize the loss, because if the loss is minimized, then the difference between the ground truth and our predictions is also minimized, right? And that will give us our desired solution. So the way we do this is we take the derivative of our loss function. Intuitively, what this means is, or what the derivative tells us is that it tells us how much each weight contributes to the overall error for each sample. And then the gradient is in the direction of increasing loss. So we take the we subtract the gradient multiplied by a learning rate, which alpha here, in order to move our weights in a direction that reduces our loss. Here's a picture of what it's actually doing. So this visualization, the z-axis is our loss function. The x and y-axis are possible weights. So this could be a linear, this could be like a single feature linear regression function, where x and y are like the bias x and the W1. And if you change the weights and the bias, then you can change the loss over the surface here. And using gradient descent, you can see it starts out in the red zone, and then after each iteration, after each subtraction, it goes down a little bit further to the global minimum. In this case, it's a global minimum because it's a paraboloid, but once we have more complex networks, then we'll most likely converge in like a local minimum. Another thing to note here is that you can notice that each step, the steps, when the slope is higher, the steps are larger. And that makes sense because if we go back to the previous slide, we're multiplying the gradient by a learning rate. So if the gradient is lower, then the steps are smaller. So it might take bigger steps when it's further away from the minimum, and the steps slowly get smaller until it converges to 0 at the minimum. So here is a quick review of what we've gone over so far. I'm gonna start a Zoom poll, see if I can get this working. Logged in. It's not letting me start the poll because it says I'm logged in from another device. Here, hold on.
I can try and launch.
Okay.
Okay, so hopefully that's showing up on your guys' end. Can we get some confirmation in the chat if that's the case? Awesome, thanks.
Yeah.
Okay. I think that's enough time.
Yeah. All right. See the results. So the first question, which of these best describes machine learning during training? And that is the majority of you guys got it correct. It is data plus output equals program. And the reason for this is that the question or the answer A, data plus program equals output, that's more like traditional programming where you have a data set and you want to do something with it to produce an output, like predicting the current day's temperature based off of other information about that day. And you'd want to write an algorithm, that program, to compute, like, oh, we know that we have a model that shows that, let's say, the humidity is inversely proportional to the temperature or something like that. So like if it gets colder, then it's also less humid, and it's more humid, then it's usually hotter. So you would write a program that uses that model to produce a prediction of the temperature. Whereas machine learning, we're taking just the raw information, the humidity data and the temperature data, and we're using that to optimize a function that hopefully at the end describes something similar to what we did with that model for question A. For question 2, the output of linear regression is continuous and any real number. Those are the two answers. So I don't know if you guys maybe got confused and thought it was like a single choice, but you're supposed to select B and C. Linear regression produces a continuous output. It's any real number, and it's not restricted to only 0 and 1. We'll see that later on. Discrete outputs are reserved for classification problems, but linear regression is more suited to regression problems that need a continuous output, like predicting the temperature. Question 3, gradient descent blank the cost function. And pretty much everyone got that right. It minimizes the cost function. Now, I mean, you could multiply the cost function by -1 and then it would be maximizing it. But the convention for us that we're going to be following is minimizing the cost function. So that's correct. Thank you. At this point, I think if you guys have any questions, you can unmute and ask. You can also do that like during these slides as well. You don't have to wait until we get into one of these review sections. Or if you ask in the chat. I haven't been monitoring it, but I think Paymon has been answering questions. So let's move on. Classification models. So up until this point, we've been mostly talking about regression. So like I said, regression is we're taking various inputs and then producing a continuous value output. Classification models are a little different in that the output is discrete. So it goes back to that the question that we had in the last slide. The outputs are either binary for cancer detection, for example, like we want to determine from this scan, like is that tumor cancerous, yes or no. We can also use it for digit classification, and that was one of the earlier slides you saw. Like the MNIST data set is a data set of hand-drawn numbers, and we want to classify for every hand-drawn number, what digit is it? Like 0, 1, 2, 3, all the way to 9. And it can only be one of those 10 classes. It can't be anything in between or outside of it. You can also do object classification. So this is like maybe you take a picture of a dog or a picture of various animals, and you want to classify what kind of animal it is. Is it a dog? Is it a cat? Is it a walrus? I don't know. So you can have more than 10 classes. But the idea is that what's in common with all of these is that this output is discrete, and it can only be one of a certain number of classes. And that's why it's called classification. So how do we do that? We can actually do something very similar to linear regression with logistic regression. The equation for that is exactly the same as linear regression, except that we apply an activation function to it. The activation function is a nonlinear function. For binary classification, you can use sigmoid. This is a picture of the sigmoid function, actually, right here from Wikipedia. So what sigmoid does is, if you recall, linear regression outputs a value, any real number from -infinity to infinity, and we want to map it to a probability, right? If we're doing binary classification, we want to map it. We want to like determine whether or not there is cancer in the picture. So with binary classification, we want a probability from 0 to 1. That's what sigmoid gives us. For multi-class classification, we have softmax, which is a generalization of sigmoid to multiple classes. Basically, you can only, let's say you had 10 classes. The sum of all of those probabilities will have to equal 1. And it's basically giving you a distribution of what it might be. So like if you had a digit that might look similar to the digit 9, then that could be like maybe 90% the digit 9, and then it might look a little bit like another number, I'm not sure, like 4 or something. So that could be another 10%. But the sum will always be 1, and that's what softmax does. This activation function, oh yeah, this is pretty much what I just said. It's the same as linear regression, except that it has an activation function. And the activation function maps that space from -infinity to infinity to 0 to 1 for sigmoid or softmax. And that's kind of the gist of it for logistic regression. If you're coming from beginner track, this is actually where you would end off at the end of the workshop. You'll go a little bit more in depth on logistic regression and talk about how to use that to make predictions. Does anybody have any questions up until this point? If not, then we can move on. There's actually another, oh yeah, go ahead.
Before we do, can we just get a gauge on how the pacing is for everybody? If you're comfortable, you can unmute yourself or just put it in the chat if it's too fast, too slow, just right.
I'm comfortable with the pacing.
Sorry, I missed what you said.
Personally, I'm comfortable with the pacing.
Okay.
Awesome.
Thanks.
Yeah, it was pretty good.
Awesome, thanks.
Thank you. All right, that's good. In that case, I think we can move on. If we have some extra time, I think I might want to go back to a couple slides and maybe elaborate on that. But we have another review, just a couple questions this time, but it's about what we just talked about here. Yeah, it's still not letting me do the poll, so just then, thank you. We could probably cap it at maybe like 80% or more, just so we don't take too much time. All right. So the first one is a bit of a trick question. So I gave you two, there are two choices. Which of these is a regression problem? A is predicting the amount of rainfall in inches based off the temperature, and B is predicting whether or not it will rain tomorrow based on temperature. So they're very similar, but it sounds like B would be a classification problem, and it can be a classification problem, probably would be considered one. But the reason is you can also kind of consider it a regression problem, because the definition of regression is that the output is continuous. And technically, producing a probability between 0 and 1 is still continuous. That's also the reason why it's called logistic regression and not logistic classification. So you could consider that as a regression problem, but for our intents and purposes, we're probably going to call it like a classification problem. A is definitely a regression problem because we want the amount of rainfall in inches, and that's continuous. And I also said that earlier that linear regression can be any real number, but it doesn't mean that like it has to make sense for any real number. So the amount of rainfall can't be negative in this case, right? So it wouldn't make sense to have an output that's negative, but it can produce one. It's kind of the idea behind linear regression. And the output for logistic regression, the second question, is discrete and only numbers between 0 and 1. It's actually continuous because, like I said, it produces a number between 0 and 1, and that's a continuous scale. But usually when you have, what you would eventually do with that probability is make a decision boundary, right? We want to decide, whether or not it will rain, not, oh, it's gonna rain 50% chance or something. Although weather apps actually do that. They tell you a percentage chance of rain. But at the end of the day, it's usually considered discrete, but continuous also works.
And we can even go back and show that in the diagram, I think a couple slides back, if that can help explain.
I think I can select, yeah, this is easier. It will be previous.
Slide 28 for me.
Oh, 28, got it, thanks. Oh, wait. Are you talking about the slide?
This is correct.
Is correct?
Yeah.
Oh, yeah. Thanks. Oh, sorry. I was looking at the wrong slide.
Ben, you want to go ahead and...
Oh, yeah, sorry. Yeah, so you can see that it is still continuous between 0 and 1, the sigmoid function, this diagram. That's why it's considered continuous.
Yeah, so if I can say something about that. So basically, like, what would happen is you apply this activation function, right? So if you want to say whether it's going to rain or not, so let's say the way we discretize this output is if the result is less than 0.5, then we'll say no, like we'll say our model says no, it's not going to rain. But if it's between 0.5 and 1, we'll say yes, it's going to rain. So the idea is, although logistic regression is going to give us some discrete or some continuous output space, we usually discretize the output space ourselves based on some boundary condition that we define. So in this case, although we have continuous outputs of any real number between 0 and 1, we're going to discretize that into no and yes based on based on boundaries, right? So that's kind of what we're doing. That's what we're talking about here with logistic regression. So yeah.
Thank you. Actually, another thing is, you might notice with the sigmoid function, it reaches 0.5 at exactly 0. So basically, that kind of gives us a natural threshold point or cutoff point where you could make it yes above 0.5 and no below 0.5. And so like any negative number produced by linear regression would be considered less than 0.5, and any positive number is above 0.5. So we can go back to right review. And yes, it's only numbers between 0 and 1 because we have that activation function and not any real number. All right, so now we're going to go into neural networks. Just a brief introduction before next workshop, we're going to go a lot more in depth about things like backpropagation. In this slide, we have sort of a diagram of what a kind of a vanilla neural network looks like. Each of these circles is called a neuron, maybe except the input layer. Those are just values. So each of those circles is like one of those features that we mentioned before. And each of the circles in the blue and green squares are neurons. A neural network can have like multiple neurons per layer and has multiple layers. And this is sort of why it's called a neural network. It's roughly modeled off of, or roughly inspired by how real neurons or like biological neurons work, but it's it's a rough approximation. So each of these neurons is an artificial neuron, is what we call them. And it's actually very similar. It's exactly the same pretty much as logistic regression. That's sort of why we lead with logistic regression and go into neural networks. But each of these neurons has its own weights vector that's independent of other neurons. And it has its own, and it has an activation function, which might be something like sigmoid as well. If you recall, the logistic regression equation is y equals sigma x times the weights plus the bias. In this case, we have it in vector form. So the weights actually should be in front, I think. But it's a matrix, and then the x is also a vector, and y is also a vector. So it's not just a single output. Actually, no, sorry. That would be, I think it is a single value, sorry. It is not a vector. I might be wrong. But, yeah. But you can kind of think of logistic regression as a perceptron in the left diagram here, but it's not exactly the same. Like if you Google what's the difference between logistic regression and perceptrons, there are subtle differences, but for our purposes, we're going to consider them kind of the same thing. But the difference between what we've done so far with logistic regression and neural networks is that just we've kind of combined multiple logistic regression nodes, and we feed the output of one node to the next layer, and that's what makes it a neural network versus just logistic regression.
So to kind of give an example of this, so with the perceptron, right? Let's say we're doing the thing. Let's say we're trying to solve the task of, is it going to rain tomorrow, right? And it's like a binary classification task, and we can use any number of features given whatever data we have in order to try to predict this, right? So in this diagram with the perceptron, we have like, think of the 4 blue dots as our inputs, right? So it says input layer. So we can think of each of these as a feature. So for example, we can say one of these features can be the humidity. Another one can be, it can be anything that is pertinent to like whether or not it's going to rain tomorrow. So like humidity, temperature, and then think of any other 2 features, right? So then we're going to use all of these different features in order to basically give this output. And if you remember, if you look at the equation, right, we have the y equals wx plus b, right? So the weights kind of dictate, as the name suggests, how important each of these features are in determining the output. So if we were to assign a weight to each of these input features, we could say hypothetically that the temperature is a lot more important than the humidity when we're determining whether it's going to rain tomorrow. So the weight for the temperature feature might be like 5, but the weight for the humidity might be like 0.5. So in that sense, what our model is doing is saying, okay, I think the temperature is a lot more important. So I'm going to use that a lot more heavily when I'm predicting whether or not it's going to rain tomorrow.
Yeah.
So yeah.
Answer,
Yeah, go ahead.
I was going to answer the next question in chat. So one person asks, each layer is sort of a different level of decision. So is it cumulative? So what each layer does, as we'll kind of see later, each layer kind of learns higher level features. So the deeper you go, it's building off of the outputs of the previous layers. Especially with like, I think it's especially, you'll be able to see it with convolutional neural networks once we get to that workshop. But I'll kind of talk about that example. So like a lower layer might learn kind of basic features about the data, or basic relationships between these different features, right? It can learn information like, okay, well, there's a relationship between, I don't want to go back to the rainfall example. I'm going to go to like housing prices. So with housing prices, there's a lot of factors like the area or like zip code it's located in, the size, and the footprint, how many levels is it, how many windows does it have, and a lot of this information is related. So a lower level layer might learn basic relationships between those things, but once you get up one level above that, it can learn relationships between those relationships, right? So those neurons would encode higher level information. With convolutional networks that we'll see later, you'll see that like the lower level neurons are gonna learn small features like, oh, this is a line, or this is a corner, or this is a boundary between two colors. And the higher level neurons that are deeper into the network are gonna learn more complex features like, okay, well, if we put two lines together, we get a corner. So it's kind of like taking small building blocks at the lower levels and then building up into um, the final prediction at the output layer.
Yeah, so that's a great way to think about it. So we usually like to explain it exactly like Ben said, of how it you're taking abstract pieces of some certain feature space, and then you're using that in order to give the output. So basically what I remember when I taught this workshop, something I said last time I taught it was that when you have this like one layer perceptron, I kind of think of it as if your bandwidth or your potential to learn certain relationships between objects is very limited, right? So, and that's intuitively that makes sense, right? Because you have a very small model, you'd anticipate that it'd be less powerful and it'd be less capable of learning more complex relationships. So when you have a small model, like in this very simple case, like this perceptron we have on the left, you can it's useful for some tasks, right? Like we explored some tasks earlier in the workshops that maybe you could just use a perceptron, some very simple things that have very like obvious answers. Maybe you can use a very simple model, and that might actually be more beneficial for your use case, because maybe you really need whatever task you're using this project or this machine learning model to work really quickly. So then you need a very simple model so you can very quickly compute a prediction. But maybe you have a much more complicated problem. So one example of that would be something that Ben said earlier. Like, let's say we're trying to, given an image, we're trying to predict, I don't know, what kind of animal is it, right? Like, is it a dog, cat? Is it a weasel? What is it, right? So there's a lot more nuance that goes into predicting things like that versus like if a number is a 1, a 2, or a 3 or 4, right? There's a lot more nuance that goes into it. Like with a number, as a human, you can kind of point out some things that might give it away. Like the 9, it has a little loop at the top and has a line at the bottom. It's a lot harder to say that those sorts of things for more complex examples like identifying animals. And that's where these heavier, deep neural networks come in. They have a lot more layers, like the one on the right. Like usually a neural network is going to be much larger than this. But even in this case, it has a lot more bandwidth is the word I like to use than our perceptron on the left. It has a lot more capability to learn a lot more nuanced features. And this makes a lot of sense, right? Like you can see, obviously, there's a lot more arrows pointing to a lot more different things. Each of these arrows has a weight associated with it that's basically saying this feature, it should be this important when going to the next layer, and so on and so forth, right? So, and then as Ben said, these features encode abstract information. So a lot of times it can be something simple like, oh, maybe that 9 has a loop in it or there's a line under it. But a lot of times what the network's actually doing is it's learning relationships that we don't necessarily think of as humans. As humans, it's really easy for us to look at a 9 and be like, oh, there's a loop there and a line under. But a neural network might learn relationships in a way that us as humans don't think about. Like it's easy to think of like, okay, maybe I can identify a cat as having like pointier ears than a dog or something. And that's maybe something you would describe the distinguishment between a dog and a cat as a human. But a neural network often learns things in a much more abstract sense. So you might not necessarily be able to understand what that feature is just by looking at it if you're a human. Sometimes you can, sometimes you can't. Generally speaking, if it's a more simple problem, you're going to be able to, but the more complex the problems get, it's a lot harder it becomes to see, for example, like what feature is actually being encoded by this like middle hidden layer, right? That's often a very difficult question to answer. So that's just something I thought I would clear up.
Yeah, actually, to build off of that and lead into the next slide, we're going to talk about why bother with all of this? Why bother with neural networks instead of perceptrons or logistic regression? That's basically the same thing that Paymon said. It lets us model more complex data. Paymon used the term bandwidth, but another term that I've heard used is neural networks have more representational power. They can represent more complex relationships between with data than just like simple logistic regression. If we go back to let's see if I can find it. What is linear regression? This is linear regression, but you notice that the logistic regression is based off of linear regression. It's actually considered a linear classifier. So it can really only learn linear decision boundaries. It can only draw a line between this data. So this is linear regression, so we're trying to fit the line to the data, but logistic regression might have like dots on either side that are different colors, and then you try to draw a line in between. Actually, let me draw it out since we have time. But with logistic regression, we're really limited in the kinds of relationships that we can represent. And with neural networks, we have a lot more a lot more flexibility in what we can do. So let's see if I can draw this.
Ben, are you drawing on the iPad?
Yeah.
Oh, okay. Okay.
I think you guys can see it, right?
Yeah.
Okay.
You're good.
So let's say we had data points here, here, here. And then we had green here, 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 here. With logistic regression, it's still learning a linear decision boundary, right? It's still going to have to eventually draw a line that cuts through that data and goes, everything beneath that line is one category, everything above that line is another category, at least for binary classification. But but let's say the data looks a little bit different, right? If it looks something like this, where we have dots here and then red dots here. Now this is not if we draw a line through it with like blue, we're still gonna cut off, like there's still gonna be some mispredictions. Actually, this one's pretty good, but like if it's even worse, like the red dots, there's a bunch around here, then you can't really model that. You can't really draw a line that cleanly separates those two points, those two sets of points with logistic regression because it's a linear classifier. With neural networks, by layering linear classifiers together, but with activation function, so it's nonlinear, you can make a more detailed, let me draw a pen. You can make a more detailed decision boundary that correctly classifies more of those data points than a linear classifier can do it. But there is a trade-off here, right? I think the technical term is the bias variance trade-off. A logistic regression is a very simple model. It's a linear classifier. It only draws that simple line, so it has a lot of bias, right? A lot of the predictions it makes is heavily influenced by or heavily biased by the model itself. Neural networks, depending on how many neurons it has, how deep it is, has more variance. So it has the ability to draw a more complex decision boundary here, but it's also prone to things like overfitting, right? So if you have very few data points and so maybe you have like one red dot in here, like that, a sufficiently complex neural network might draw a decision boundary that goes like this around it when that might not be desired. So there's a trade-off between using a really simple model that has a lot of bias and using a more complex model like neural networks that has a lot more variance. And that's what we'll talk about a lot more in future workshops, but that's sort of the motivation behind why we want to go into neural networks, or why logistic regression isn't enough.
Yeah, so to add to what Ben said, so there's a lot of trade-offs, right? So another thing that's important to note is if you want to be training things on more complex problems intuitively, it would make sense that you need a lot more data, right? So if you have Ben, if you could go back to the neural network slides that we were on.
Yeah, I'm going back right now.
So there's a lot more potential for representation here, but in order to adequately define that representation space, you're going to need a lot more information in the first place. And this is the core reason why Facebook and all these companies are so after and intrigued by your guys' personal data, is because you need a lot of data in order to make predictions. So for in that instance, I think a lot of it goes to like targeting ads, right? So there's a lot of machine learning, deep learning models that these companies use in order to give you guys like ads that seem interesting to you, or that they would think are interesting to you. And that's a very complex problem to answer, and it can't be solved by something as simple as like logistic regression model. So they have to develop very deep, very complex neural networks, kind of in the manner that we're describing here. A lot more complex, actually, than what we'll even be going over in this track. But they need a lot of data in order to train these models successfully. So that's why they're so after your information all the time and stuff like that. So, and that has implications for you as an individual trying to learn machine learning. You have to think about, how much data do I need if I'm going to be solving a certain problem? And you can kind of get an intuition from it based on how hard you may think the problem is to solve, right? So sometimes you're going to need a lot of data. And on top of that, the more complex model you have, the longer it takes to train, the more sophisticated and powerful hardware you're going to need to train that stuff in a reasonable amount of time. And a big thing that Ben hit on is the problem of overfitting. So to elaborate, because we have time, so to elaborate a bit more on what the idea of overfitting is, it's that we don't want to memorize the information that we're feeding to the model, right? So when we train our model, we feed it a bunch of information in order to learn for it to learn all these weights and biases. And we're going to tell you guys how it learns these weights and biases a lot more in the next workshop. But we gave it a bunch of information in order to learn these weights and biases. But the thing is, if you train it too many times, if you do too many iterations of that, it'll get so caught up on just the information that you're giving it that it'll generate a function that can only answer questions that are within things that you've already fed the model before. So then if you give it a picture that it's never seen before, then it might screw it up because it's so caught up on getting the answers correct for the things that you've been teaching it, that if you give it something it hasn't seen before, it'll get mixed up. So an analogy I like to give is, as a student, if you're really caught up on the semantics of every homework problem you're doing, and you just want to memorize exactly how to do each homework problem, then when you go take an exam, you might not perform very well because you haven't actually learned how to generalize the fundamental concepts that go into getting that question right. You just memorized, like I need to carry the 3 here or do something for this specific type of problem. But if you change it up a little bit, you'll get confused because you haven't learned to generalize. It's the same exact thing, discussion that we have a lot of times when we're talking about neural networks. It's a key thing and a key problem that we face as machine learning engineers is making sure we don't overfit the data. And and the idea is overfitting kind of just means you're memorizing the data you're giving it, not actually learning to generalize based on the data you're giving it. So it's not actually learning things, it's just memorizing. So
yeah. I'm just gonna. Oh, sorry. My next slide. I'm gonna continue going through the slides, but we're almost at the end actually. So I think I'm gonna go back to a couple of slides and elaborate as well after this. Yeah, so next workshop, we're gonna talk about the neural networks pipeline. By that, what we mean is going through the process of defining the architecture and then kind of the training loop, right? We're passing inputs forward, getting the prediction, computing the loss function, and then performing gradient descent to adjust the weights, and then doing backpropagation to adjust, to adjust the weights. And then going back to step 2 to pass the inputs forward again and repeat until we converge on a local minimum. If you have any questions, again, feel free to ask at any time, interrupt us and ask in chat. I want to just talk about a couple upcoming events, or just one upcoming event, which is the next workshop. We'll be mainly talking about backpropagation and talking about neural networks in more in depth than what we have today. Because it was, in more in depth than what we have today. And there's also at the last slide, if you have these slides open, there's an anonymous feedback forum and a Facebook group that you can go to. But I'll leave off on this slide for just a couple moments, and then I'm going to go back to one thing that I want to touch on. Or if you have any questions, let me know so I can actually go back to a specific slide and talk about that.
Yeah, this is the last slide. So if you guys have the slides open from the beginning, it's there.
All right. I'm going to go back to actually gradient descent, because I feel like I neglected to talk about this in enough detail. One particular thing is, like, I told you guys that the gradient is tells you how much each particular weight contributes to the loss, but I don't think it's exactly clear. I'm not sure if I made it clear that clear why or how it contributes to it. So I'm gonna draw a really quick diagram here, and this plot is the loss. Oops, did not mean to click. The loss function, and the x-axis is just the weight. And the loss looks something like this. So this is similar to this slide, actually. I'll leave here. So this is the same thing, but in 2D, and the weights are the x-axis. If we're at a point here, and let's say that's 2 for the weight and 5 for the loss. If we take the gradient, if you notice the slope, it's negative here, and it's positive over here. So in order to minimize the loss, the slope, DL, and then over here, it's this slope is +1. Over here on the left side, we want it to be, we want to increase the weight, increase the value of the weight in order to go to the local minimum. And we do that by taking the negative of the gradient. And similarly, if we're on the right side, then we want to go the opposite direction. So we want to do -1 instead of +1.
Yeah,
And that's why,
we've been using the word gradient a lot. So I'm not sure, like, if you guys haven't taken a multivariable like calculus class or something, maybe that concept isn't familiar. So we define the gradient as kind of the direction you have to move along this topology of this function to basically increase the fastest, right? So you're saying, okay, I want to, so for example, in this little paraboloid that we have, this animation, so the gradient would tell you, okay, we need to move like in a certain direction, like towards those more red points in order to increase our value the fastest, right? So that's the exact opposite of what we're trying to do, right? But we can use that information because it is the exact opposite, right? So if we know that the gradient tells us the direction to move in order to increase the fastest, Well, we want the direction to move to decrease the fastest, which definitionally is the exact opposite direction, right? So we take the negative gradient in order to basically find the direction we should move along this topology in order to get to that minimum the fastest. And that's exactly what we're doing when we're training a neural network. Because when we're training a neural network, we're trying to learn a function. And the things that are initially unknown are these weights and bias values. So the network is learning these weight and bias values in order to minimize this loss function, right? So what we're doing is at each step of the process, every time we feed it an input and then it tells us its prediction, then we compute the loss. We're saying, okay, how do we change the weights and biases to decrease the loss? And decreasing the loss is what brings us to this local minimum, right? So eventually, if we decrease the loss more and more and more, by the definition of how we define the loss, once our loss is at 0, that means we're classifying everything correctly, right? Just based on the way we define the loss. Because the more times we get the answer wrong or the farther away we are from the correct answer, the greater our loss. So if we decrease the loss down to 0, that must mean we're getting everything right, or we're getting close to everything right if it's very close to 0. So that's why we want to minimize the loss function as much as possible. Just thought I'd clear that up.
Okay. One question was, I think I wasn't clear on exactly what we're updating. So we're calculating the gradient. Let me go back to this slide. So the gradient is the derivative of the loss with respect to each of the weights. So by each weight, what I mean is in the weights, the weights might be a vector, right? And we want to take the derivative with respect to each of those weights. And each of those partial derivatives will tell us the sort of the contribution of that weight to the loss. So if that was positive, then that means we need to reduce that weight in order to reduce the loss. Does that make sense?
So the things we're modifying are the weights in the network. Okay, so those are called learnable parameters. So we give it kind of this kind of skeletal. There's kind of this skeletal structure that we have, right? When we first look at the neural network. So like Ben, if you could go back to the neural network.
I'm going to hypothesis function.
Yeah, actually, could you go to the visual of the neural networks for me?
Okay.
Yeah. So when you first initialize, so this is fine. So if you guys recall, kind of what happens when we look at each of these artificial neurons is you can think of it as a little perceptron, right? And we're just kind of combining a bunch of perceptrons together in order to create this deep neural network, right? So, and then what's happening at each step is what we discussed at the beginning of the workshop, how you're kind of performing this logistic regression task, right? So you kind of have that skeletal structure of the function of, okay, there's a W1x plus a W2x plus a W3x plus some B. And the X's are the input data that we're feeding into the model. The W1s, the W2s, the W3s, et cetera, and then the bias, those are learnable parameters. So those are the things that the network actually gets to toy around with in order to basically figure out what function is best going to predict our output.
Yeah, this is sort of similar. This is why we say we're taking the input and the output and producing a program out of that. That's because we're kind of fixing the input and output. We're not, and then we're adjusting the weights of the model itself. So going back to.
So I think there's a question in the chat.
Oh, there's. Okay.
It says, what's the difference between a perceptron and logistic regression? So, logistic regression is kind of an idea. Like it's kind of a concept, an idea we use that we discuss. And then the perceptron is a specific kind of model. It's that very simple model where you have these input features, and then we use these input features, assign a weight to each of them, and then try to predict our output. So we have a diagram of the perceptron. I think it's on the next slide, Ben, or is
it's it's a few slides over. Here it is.
Yeah. So this in and of itself is the perceptron. And you could say that the perceptron utilizes logistic regression in order to function, right? like this is the same way that you guys have probably heard of a convolutional neural network and these other buzzwords thrown around. These are all types of models, right? And there's specific concepts behind each of these models. Logistic regression is just one of the concepts that these models utilize in order to do their jobs.
Yeah, there's also some subtle differences between how people use those two terms.
Yeah.
For our purposes, they're going to be the same, but if you Google it, there's actually like a statistics stack exchange question asking this exact question, and they go in a lot more into detail about like why there is a difference, but for our purposes, we're going to consider them kind of the same thing.
Yeah, like we have if you guys are super interested in the difference between these things, like we have classes on campus taught by faculty that kind of dive into the differences between these things and give really rigorous mathematical proofs and stuff. And actually, to some extent in the future, in our next workshops, we're going to be looking at some much more rigorous mathematical explanations behind exactly how neural networks work, how they make predictions, and how we're going to predict things. So yeah.
Yeah. To answer your question on the gradient or how I calculated it, we're going to go a lot more in depth in the next workshop with backpropagation of like exactly. We're going to calculate it by hand and show you where it comes from, but to give you a preview, or because it's not exactly clear on this slide, y hat here is the prediction, right? So y hat is actually, oh, am I not writing? Okay, there we go. Y hat I, it's the hypothesis function of xi, and then of course the weights. So the hypothesis function from a previous slide right here, it has x in it, right? So if we have it, so it's really yi is equal to b plus w1 x1, and then once we go to the gradient, we can substitute that into yi here. So once you take the derivative, or let me go this slide. Yeah, so once you take the derivative, right, you do chain rule. The 2 goes out here, and then the derivative of this is just x1, and that's where the x comes from.
Yeah, this will be a lot more clear next week.
Yeah, I didn't intend to write on this slide, so that's why it's kind of messy here. But next week we'll definitely have this a lot more detail.
So let me answer Joshua's question. I think someone else was trying to ask a question too. Is the hypothesis function necessarily linear, assuming we are using logistic regression? So if you're just looking at a perceptron, right, the function itself is linear. But when it comes to a multi-layer kind of neural network, right, you're kind of stacking a lot of linear pieces into each other. So it's no longer just a linear model. It's a lot more complicated than that. And that's kind of why when Ben was kind of drawing that visual of you guys, between the limitations of like a logistic regression model. So the logistic regression model, right, it created that line for us that could kind of discretize, it created like a hyperplane that kind of splits the space into 2 pieces, where one side of it is going to be like one classification, the other side's going to be the other classification. And that's like that's just a straight line, right? But when we get to these more complex models, you're no longer just dealing with a linear function necessarily.
And to answer Darren's question, is x representing a constant? Yes, we're holding the inputs and the outputs constant in this case. The only thing we're varying are the weights. So that's why it acts like a constant when we're taking the derivative. in this case, we're taking the derivative with respect to the weight, so it would be constant even if they did change.
Yeah, right. It's a partial derivative, right?
Yeah.
So so for what do you mean? So a multivar each weight is linear. The weights. So Joshua, the weights are just values, right? And we're like, the weights in them of themselves are just values. They're not actually functions, right? So like I was saying, if you want a concrete example of like how the weights are used, right? So if you're doing that rain example of whether it's going to rain tomorrow, if you have like 4 features, like temperature, humidity, and then some third and fourth features, if you think the temperature is a lot, if the model, I guess, learns that the temperature is a lot more important in determining whether it's going to rain tomorrow, then that weight is going to be a much larger value than for say humidity. So you might have a weight of 5 for the temperature and like a weight of 1 for the humidity, and those two numbers are something the network learns over time. So we'll learn where to start and good ways and good places to initialize those weights, but over time the whole point is the network learns by changing those values, and those values are just constant value. Well, they're constant in the sense that they're singular values, but they change over time as the model learns.
Yeah. So when we initialize our weights, we just do it random. There's different ways you can do it, but random works well.
So for the sake of, there's certain ways you can initialize the weights such that you're more likely to be closer to where they should be, but in the most basic sense, you just initialize them to random values, right? So like I was saying earlier, you kind of have this empty skeleton of your neural network. You know, for example, in that visual that you're going to have a certain amount of inputs, and you know you're going to have a certain amount of artificial neurons in the middle, and you're going to have a certain amount of outputs, right? Like for example, for the if you're trying to classify handwritten digits, right? You already know ahead of time there's going to be 10 different outputs, right? So we know that, and we also know our input's going to be an image, and we are going to discuss more in the future like how you can represent that. You guys can probably imagine, right? It's an image. Images are just pixels. Pixels have numerical information that encodes them. You just kind of take that numerical information. So you have your inputs and your outputs. You kind of decide ahead of time, okay, this is how large I want my network to be. This is how many hidden layers I want to have, how many neurons I want to have. You kind of choose that yourself. And then what the model's job is to kind of, given that skeleton structure that you've created, it's kind of supposed to learn all those weights and biases. So something that we're going to be touching on a lot in the future is that there's a lot of parameters that you as the engineer actually have to decide yourself, and that the model doesn't learn. And these are called hyperparameters. But so there's the distinction between learnable parameters, which are the job of the model themselves to learn, and hyperparameters, which are things that us as engineers kind of toy with and tweak around in order to improve the efficiency of the model. And for the sake of this workshop series, the learnable parameters that we'll be looking at are generally always going to be the weights and the biases. Hyperparameters are stuff like the learning rate that Ben briefly touched on, which we're going to explain what these things are in the future, so don't worry about that. But there's a lot of things we have to choose, and there's a lot of things the network has to choose. So it's kind of a team effort in that sense. So
is there any other questions?
yeah, so I was gonna say, so we've kind of gone over everything we had for this first workshop. This workshop was just meant to be kind of a very high level overview, mostly a review of things you guys have hopefully possibly seen before. And if you guys haven't, then like hopefully like you learned some of that stuff. And next week we're going to be diving into things that like we don't expect that you guys have ever seen before, and like we're going to talk about these things a lot more rigorously behind the math, and give a lot more structure to all these variables that we kind of just like threw at you guys today. So don't worry if not everything makes sense right now. The point of this was kind of to develop a high level intuition of what's going on in the machine learning space, and we're gonna delve into the semantics a lot more starting next week. If you guys have any future questions, please, like we said earlier, please hit up the Discord, or just like ask us right now. But other than that, like we can wrap it up. But Trevor has a question.
Oh yeah.
Error function have yeah, so that's something Ben actually briefly mentioned at some point. So in that, Ben, can you go back to that
Yeah. I'm
3D
trying
animation?
to. It's not okay. There we go.
Let's also repeat the question for those watching the
Yeah.
recording.
So
Yeah.
can an error function have multiple local minimums for gradient descent? So yeah, it almost always is going to have multiple local minimums, right? It's actually like next to like 0% chance that your model is going to converge on the absolute minimum of the function. It's very unlikely. So what usually happens is you're going to meet some local minimum. And you might be asked, I think a question that naturally is asked after that is, if you're going to converge on some local minimum, how do we know that we're not just like converging on some like little dip that just happens somewhere where right next to it there's like a really big dip, and we would much rather get to that really big dip, right? Because by definition that means our loss is a lot lower, and that by definition means our model is classifying things a lot better, right? So how do we make sure we don't get stuck in these little divots that may be along the topology of the function? And that's actually part of what I was discussing with hyperparameters. Us as the engineers can toy around with hyperparameters that kind of determine just how much we should be moving at one step at a time. Because in reality, the function isn't going to be some like little smooth thing, that some little bowl that's some nice paraboloid that we have in the animation. That's great for just understanding. But in reality, the function not only is impossible for humans to visualize because it's usually much larger than a three-dimensional space because we have many, many features, but it's also just much more complicated and confusing. So, and there's going to be a lot of little dips that we kind of have to overcome and make sure we don't get stuck in. So there's ways that we can kind of deal with that, and that's mostly dealt with using the learning rate. The learning rate kind of determines how much we should jump, how aggressively should we tune our weights at each step, and we're going to talk about that more next week. So that's a great question.
Yeah. Another way is not just changing the learning rate, but also gradient descent, or the gradient descent that we showed, where you just take the average of all of our samples, is not the only way to do optimization. There's other algorithms as well that are that kind of help with this problem. Things like ATOM, or like like when you're doing machine learning with PyTorch or something, you might see that the fault is usually ATOM or something, and that's a variation of it's similar to gradient descent, but it's not exactly the same, and it solves some of these problems.
Yeah, there's a lot of different optimization methods we can use. Exactly.
Right.
Gradient descent is just one of them that
Mhm.
specifically we're going to be showing you guys about stochastic gradient descent, SGD. It's a very common optimization criteria that is used in basic machine learning. So that's what we're going to be touching on. Samuel had a question. Can you go to slide 24, Ben? In slide 24,
24.
how does subtracting the derivative of the loss function, which has a y component, from the weights, which is on the x-axis, get it closer to the ideal weight? Or does the coefficient alpha reduce the gradient to just an x component? Is this slide 24? Oh, the coefficient alpha is the learning rate, actually. So yeah, you go ahead, Ben.
Oh yeah, no, I was just gonna say that we're going. This is or what we're showing here is just element by element. So we're adjusting the weight W. So everything here are scalars, right? There's no. Let me check, make sure. I'm not.
Yeah, I mean,
Yes,
you can treat them as scalars.
Yeah, there's no vectors here. There are no components.
Yeah,
Right.
so basically, okay, first of all, we're going to give you guys a much more rigorous breakdown of, we're going to like derive all these things in the next workshop, actually next week. It's going to be very clear. But basically, something to note is like a paradigm we're going to use when we're explaining a lot of this stuff is that A lot of times we're going to show you guys a function as it applies to a scalar or a single weight, right? Which is kind of what we're doing here. But when you actually, when the computer actually computes and does backpropagation and does all these things that run down these functions and performs the optimization, it does everything in terms of matrices and vectors and well, tensors, as we commonly refer to them in this realm. So it's usually done all at once, and we take advantage of linear algebra to do that. So next week, what you'll notice a lot of is we're gonna first show you guys an equation that works on one, just like one training example or one weight, right? So one weight, there's like in a neural network, there's like many weights in the model, right? As you guys saw in the visual earlier, if you want to go to the visual again, Ben, of the neural network.
Yeah.
There's many weights in the model, right? Okay. So if you want to see it literally, right? Every single one of these lines connecting one of these neurons to another neuron has a weight associated with it, right? And each of those weights has to be learned by the network. So when we show you guys these equations, the first thing we do is show you how it works just to get from one weight to another weight, like just across basically one of these lines, right? But then what we do is we'll extrapolate that equation and we'll kind of expand it into vectors and matrices, such that basically you can compute the entire layer at once. That's what's amazing about it, right? So how it's commonly organized, right, is that your weight, you'll have a weight, at least the way we like to explain it, is you'll have like a weight matrix for each layer, right? So you have this input layer and then you have this hidden layer, and then you have all these lines, and each line has a weight associated with it, right? All of these weights will be stored in a single data structure. And using linear algebra and just matrix multiplication, we can take advantage of certain properties of the way things are multiplied in order to compute literally all four of these outputs from this hidden layer all at once. So you just do one pass, it'll compute all of those. You do another pass, you'll get from hidden layer 1 to hidden layer 2. You do another pass, you get from the hidden layer 2 to the output layer. So it happens all at once. And that's why I'm sure maybe you guys haven't heard that machine learning is highly dependent on an understanding at a deep level of linear algebra and vector spaces and what's actually happening here, because that's actually the core reason why machine learning is possible. None of this stuff would be computationally feasible if we just wanted to go ahead and compute each of these values one at a time. It would be so infeasible. So yeah, it's really important to note that in reality, these things are not computed one at a time. So, and we're going to touch on that a lot more next week. So I think most of what we're touching on at this point is stuff that's going to be covered in the next workshop. So
Yeah, actually, sorry, I wanted to interrupt, but I think, Sammy, I reread your question. I think we might have accidentally said gradient, but this is a partial derivative, so this is just one of the components of the gradient. I think that might be what might confuse you.
Oh yeah. This
is a
value
partial.
in and of itself is not the entire gradient, right?
Oh, here we go.
The gradient is computed as a culmination of the gradient is computed as a culmination of all of these little partial derivatives that we calculate. And as you guys will see next week when we talk about backpropagation, you'll see kind of how we use all of these partial derivatives in order to compute the final gradient. And then we use that final gradient to change all of the weights in the network in one pass. Like I said, in reality, usually things are kind of done all at once, right? It's just really hard for us to explain, okay, this all happens at once, right? So what we do to make it simpler is we say, okay, this is just one piece that's happening one at a time, and then we bring it all together later. So yeah. So Ben is kind of
I'm trying to
that up.
But there you go.
Yeah,
that's kind of what I was going to show. That's really bad.
Yeah. So if there's no other questions, I think we can probably wrap it up here.
Mhm.
I think we've covered everything we wanted to cover for this workshop. I really appreciate you guys coming out once again. Next week, we're going to be talking about the math behind backpropagation and how neural networks actually learn. Please, if you guys have a second, please go ahead and fill out our feedback form. We really appreciate it to see how we can improve, especially with this online format. You know, we're all new to this online format, so and anything specific to that would be appreciated. Justin just posted the feedback link in the chat for you guys. It's like 2 questions. If you have time, we'd appreciate it. So yeah.
Yeah, let us know if you have any like critical feedback, if you thought like if something we did went well, or you know, you felt like the pace was too short or too fast or too slow, or you felt like there wasn't enough content or too much content. All that stuff is stuff we appreciate. Thank you.
Yeah, so I think I'm gonna go ahead and stop the recording now. If you guys want to refer back to anything that was said at any point in the workshop, you can. We're gonna be uploading